What if I told you that uh, in enterprise machine learning, taking an already incredibly expensive cluster of computing hardware and then just, bolting on 20 more massive dedicated servers to that architecture could actually cut your total cloud computing bill by nearly half?
I mean, it sounds completely absurd.
It sounds like terrible accounting. Like, it sounds like the kind of math that gets a chief technology officer immediately fired.
Oh, absolutely fired. But the thing is, in the realm of planetary scale data architecture, breaking the laws of traditional hardware economics is, well, it's often the only way to actually survive.
Yeah, and that is exactly why we're here today. Welcome to the deep dive. Today, we are tearing down the absolute bleeding edge of Google Cloud machine learning infrastructure.
And it is a phenomenal paradox to start with because, it forces you to stop thinking about computers as just isolated boxes sitting on a desk somewhere.
Right.
You have to start thinking about them as these fluid networks where time is literally the most expensive variable in the entire equation. Because when you are operating at the scale of terabytes and like petabytes, the actual physical physics of moving data around becomes your primary enemy.
Your worst nightmare, really. And that is our mission for you today. We are skipping the beginner concepts entirely.
Yeah, no one-on-one stuff today.
Exactly. We are assuming you know what a neural network is, you know Python, you understand backpropagation. You, the listener, are here because you want to know how to actually orchestrate this chaos at an enterprise level.
Right, the real-world stuff.
So our sources for this deep dive are a comprehensive, highly technical stack of Google Cloud architectural slides, and those are paired with a massive bank of real-world, highly granular scenarios.
And these aren't just hypotheticals, right?
No, these are actual stress test questions used to evaluate professional machine learning engineers. We are going to use these specific scenarios to basically reverse engineer the exact mechanics of how you build, how you track, and how you scale custom ML pipelines without bottlenecking your data or, completely bankrupting your entire department.
Which is really the most pragmatic way to approach this, I think.
Yeah.
Because theoretical architecture is honestly kind of useless until it hits the friction of a real-world constraint.
Oh, for sure.
So the scenarios we are pulling from are going to show us exactly what happens when your GPUs are just starving for data. Or, when your distributed training nodes start literally tripping over their own network cables.
Okay, let's unpack this. And I want to start with a decision that happens way before you even provision a single virtual machine. It's that foundational choice of how much control you actually need.
The big crossroads.
Right. Because if I'm leading an engineering team and someone hands me a business problem, say classifying customer service emails, my very first instinct as a developer is usually to just open up an IDE and start writing a custom neural network from scratch.
Because you want total control.
I want total control. But looking at the sources we have, they lay out this thing called the ML spectrum, and it strongly suggests that diving straight into custom code is often a massive mistake.
Oh, wait. It is a textbook example of engineering hubris. I see it all the time. It is the fastest way to just accumulate massive technical debt.
Really?
Yeah. The ML spectrum is essentially a gradient, right? A gradient of control versus operational overhead. On the far left, you have completely pre-trained APIs. Think of things like the natural language API or the vision API.
So I don't train anything there.
You don't train anything at all? You don't even bring your own data? You're essentially just making a REST API call to a model that Google has already spent millions of dollars training on, like billions of parameters.
So I just hand it an image, and it hands me back a JSON payload telling me what objects it found.
Exactly. It's instant utility.
Right. But those are black boxes. Like, if I'm an enterprise, I might have highly specific proprietary data. A generic API might know what a car is, but it definitely doesn't know what my company's highly classified prototype vehicle looks like.
That's a very fair point.
So if I have to use my own data, then I have to write my own training loops, right?
Well, not necessarily, and this is where the spectrum gets really interesting. Let's say your data is primarily tabular, so rows and columns of historical transaction data, and it's currently sitting in a massive data warehouse like BigQuery.
Okay, pretty standard enterprise setup.
Right. The traditional workflow there would be to extract that data, move it over the network to a totally separate machine learning environment, train a model, and then try to somehow pipe those inferences back into the warehouse.
That sounds incredibly painful. The friction there must be immense.
It's awful. You're paying network egress costs, you're dealing with data duplication.
And if the source data updates while you're training, your model is instantly out of date anyway.
Precisely. And this introduces a concept we call data gravity. Data is heavy, right? Moving it is expensive and it's risky. So the second tier on our spectrum is BigQuery ML.
BigQuery ML, okay.
Instead of moving the data to the compute, you push the compute down to the data. If your team knows SQL, they can literally write a create model statement directly inside BigQuery.
Wait, just plain SQL?
Just SQL. The engine compiles that SQL into native machine learning tasks like linear regressions or k-means clustering, and it executes them using the underlying distributed architecture of BigQuery itself, right where the data already lives.
Okay. That is incredibly slick for tabular data. But what if my data isn't neatly organized in SQL tables? What if I have, I don't know, a massive cloud storage bucket full of raw audio files or thousands of specialized medical images?
Right.
And I need a custom model, but I don't have a team of specialized PhDs to design a bespoke convolutional neural network.
That pushes you right to the third option on the spectrum, which is AutoML. This is the low-code, high-power tier. You bring your proprietary data set, but you outsource the actual architecture design.
How does it design it for me?
AutoML utilizes something called Neural Architecture Search, or NAS. It systematically searches through a massive hyperparameter space, testing different combinations of layers, different learning rates, different regularizations, all to find the mathematically optimal model for your specific data set.
That sounds like it would take a lot of computing power.
It takes time and compute, yeah, but it requires very little actual ML expertise from your team. You just provide the labeled data.
So if pre-trained APIs give me instant utility, and BigQuery ML leverages data gravity, and AutoML literally builds the optimal neural network for my custom data, why would anyone ever choose the fourth option? Why go to full custom training? It seems like writing your own code from scratch is just inviting bugs and massive cloud bills. If AutoML exists, isn't custom training just an exercise in reinventing the wheel?
I mean, if you are building standard image classifiers or basic forecasting models, yes, custom training might be total overkill.
Right.
But you don't choose custom training to reinvent the wheel. You choose it when you need to invent an entirely new mode of transportation.
Oh, I like that.
Because AutoML is bound by the search space that Google defines. But what if you are a research team developing a completely novel neural network topology? What if your model requires highly specific custom C++ libraries to decode a proprietary streaming sensor format before the data even hits the neural network?
So AutoML just physically wouldn't be able to process those dependencies.
Exactly. Or consider scale. If you are building a recommendation engine that processes billions of real-time events per day, the generic optimizations of AutoML are eventually going to hit a ceiling.
You just outgrow it.
You outgrow it. You need absolute bare metal control over exactly how the memory is allocated on the GPUs, exactly how the gradients are calculated, and exactly how the data pipelines are structured.
And custom training gives you that.
It gives you a completely blank canvas. It requires elite engineering talent, sure, but it is the only way to push past the boundaries of prepackaged algorithms.
It's basically the difference between buying a tailored suit off the rack and actually weaving the Kevlar fibers yourself, because you know the suit needs to stop a bullet. You only weave it yourself if your life absolutely depends on it.
That is a highly accurate way to look at it. And making that choice correctly really dictates the entire architecture that follows.
Okay, so let's assume we've hit that enterprise ceiling. We have a problem that requires the bespoke Kevlar suit. We are going custom.
Okay, we're in the deep end.
This brings us to where the actual engineering happens. If I'm writing custom Python and TensorFlow, I need a place for that code to live. The sources point heavily to Vertex AI Workbench as the command center for this.
Yep, the workbench is your kitchen.
Now, as someone who has worked in data, I know that Workbench is essentially a managed Jupyter notebook. But my very first instinct is to ask, why not just run a Jupyter notebook locally on my laptop? What is the physical advantage of paying for a cloud-managed notebook?
It really comes down to identity, security, and proximity to the actual infrastructure. Let's say you run Jupyter on your local laptop, and you want to pull a terabyte of data from BigQuery to analyze it.
Okay.
You have to download credentials like a service account, JSON key, store it on your local hard drive, write authentication code, and then try to pull a terabyte of data over your local Wi-Fi.
Oh, man. That sounds awful.
It is a security nightmare and a massive I/O bottleneck.
Right, because if my laptop gets stolen at a coffee shop, the keys to the kingdom are just sitting right there in my downloads folder.
Exactly. Vertex AI Workbench solves this by running the notebook kernel securely inside your cloud environment. The instance itself assumes an identity and access management, or IAM, role.
Mhm.
The environment inherently trusts the notebook.
So no JSON keys floating around.
None. And this is why the sources highlight the native %% BigQuery magic command.
Oh, right. I saw that in the architecture slides. Let's break down how that actually works mechanically, because it looked almost too simple.
It's beautiful. Because the Workbench instance is already authenticated via IAM, you don't write any complex connection strings. You just type %% BigQuery at the very top of a cell, followed by your standard SQL query.
Then that's it.
That's it. Behind the scenes, the Jupyter kernel intercepts that command, securely passes the query directly to the BigQuery API across Google's internal high-speed network, executes the distributed search, and then physically loads the results directly into a pandas data frame in your notebook's memory.
Wow.
It happens in seconds, without a single credential ever being exposed.
And there's a highly specific scenario in our sources that tests this exact workflow. I think it's sample question 30.
Yes, the recommendation engine one.
Right. You are developing a recommendation engine for an online clothing store. The historical transaction data is massive, and it's sitting in BigQuery. You need to perform exploratory data analysis, or EDA, and the prompt explicitly demands that you minimize the cost and the development effort of running these steps.
The key constraints there are minimize cost and effort, paired with massive data. If you try to provision standalone virtual machines and manually configure the networking just to look at your data, you're completely failing the effort constraint.
It's too much overhead.
Way too much. The architectural solution is to create a Vertex AI Workbench managed notebook and just browse the tables directly from the Jupyter Lab interface using those native integrations. You are utilizing the massive compute power of BigQuery to slice the data, and the managed notebook simply acts as the lightweight class window into those results.
It keeps your team in a state of flow.
Exactly. Flow is everything.
But what happens when that flow state requires tools that aren't pre-installed? Let's say I'm in my Workbench and I'm prototyping a natural language processing model. Sample question 92 paints this exact picture.
Okay, let's hear it.
I'm working on text classification, and I suddenly realize I need a very specific external open source library, the Natural Language Toolkit, or NLTK to tokenize my text.
A very standard library, but yeah, it might not be in the base image.
Right. And in a massive enterprise environment, installing new software is usually a bureaucratic nightmare. I'd normally have to write a Docker file, submit it to a CI/CD pipeline, wait for the security scan, and deploy a whole new container just to get one library.
Which would completely destroy your prototyping momentum.
Yeah.
And that is a very common trap engineers fall into. They assume cloud infrastructure is always rigidly locked down like production.
So I don't have to build a new container.
No, because Workbench is designed for rapid iteration. The correct solution here relies on understanding how Jupyter kernels interact with the underlying container. To get that library instantly, you simply run !pip install nltk-user directly inside the notebook cell.
Okay, I want to dissect that command because the syntax is important. The exclamation point tells the Jupyter kernel to escape Python and run this as a bash shell command. But why the -- user flag? Why is that specific detail so critical?
That is the crucial mechanical detail that trips people up. A managed notebook runs inside a Docker container. If you just type pip install nltk, pip attempts to install the library into the system-wide Python directories.
And I'm guessing I don't have permission to do that.
Correct. Because you are not the root user of that managed container, the operating system will block you with a permissions error. By appending the -- user flag, you instruct pip to install the binaries into your specific user directory, typically .local/bin, which you have full write access to. It bypasses the system-level restrictions entirely, installs the dependency in seconds, and lets you continue prototyping without ever leaving the cell.
It's all about speed of iteration during that prototype phase, but what if you aren't starting from a blank slate? What if you are migrating an existing massive legacy system?
Migrations are always messy.
Yeah, and sample question 34 brings up a really fascinating constraint. You work for a startup. Your current data science workloads are heavily reliant on PySpark, and they are currently running on physical server racks on premises.
Okay, classic on-prem Hadoop setup.
The team wants to move to Google Cloud, but they need a proof of concept with minimal effort. Now, my first thought looking at that is, well, we are on Google Cloud now, so we need to rewrite all that PySpark code into raw Python or TensorFlow to run on Vertex.
And that exact thought is what the scenario is testing you to avoid. Rewriting legacy code is the absolute definition of high effort and high risk. If you have complex PySpark directed acyclic graphs or DAGs already functioning, you do not throw them away.
So what do you do?
Google Cloud's architecture accommodates this through Dataproc, which is their managed Spark and Hadoop service.
So how does Dataproc interact with Workbench? Do my data scientists have to learn a whole new interface or log into a new system?
No, and that's the beauty of the integration. The architectural move is to spin up a standard Dataproc cluster, so a master node and several worker nodes. Then you configure a Vertex AI Workbench instance to run directly on top of that Dataproc cluster.
Wait, so the notebook is attached to the cluster?
Yes, your data scientists log in, and they see the exact same comfortable Jupyter environment they're used to. But mechanically, when they execute a PySpark cell, the Workbench kernel transparently pushes that workload down to the Dataproc master node, which then distributes the execution across the Hadoop workers.
Oh, that's wild. It's an illusion. They feel like they are just working on a single laptop, but their code is physically executing across a massive distributed cluster of machines. You've lifted and shifted the legacy code without changing a single line of business logic.
Exactly. It fulfills the prompt's requirement for minimal effort perfectly.
Okay, so Workbench is clearly the ultimate sandbox. We can query terabytes of data securely, we can inject dependencies on the fly, and we can even orchestrate massive Hadoop clusters from it. But this brings up a logistical question regarding the actual training of deep neural networks.
Which is a whole different beast.
Right. Let's say I've perfected my custom Python script in Workbench. I've tested it on a small sample of data. It works perfectly. Now it's time to train this model on, say, 50 terabytes of images, which is going to take a week of solid computational crunching.
Okay.
Do I just hit run in my Jupyter cell, leave my laptop open on my kitchen table, and pray my Wi-Fi doesn't drop for 7 days?
I mean, it is a terrifying thought, but absolutely not. Please do not do that. And this highlights a really critical conceptual divide in cloud architecture: the strict separation between the development environment and the training environment.
They are two totally different things.
Fundamentally different. Workbench is your development environment. It is an interactive, stateful sandbox. It is meant for you to be actively engaged with it. But when it is time to perform heavy, asynchronous computation, you must transition to Vertex AI Training.
So I am physically moving the code out of the notebook.
Correct. You package your Python code into a Docker container, or you can let Vertex do it for you, and you submit that package as a formal job to Vertex AI Training.
And what does Vertex AI Training do with it?
You define the hardware you want, say 8 NVIDIA GPUs, and you submit the payload. Google Cloud's infrastructure takes over entirely. It provisions those highly expensive GPUs, loads your container, mounts your massive cloud storage datasets, and executes the training loop.
So I can close my laptop.
You can close your laptop. You can go on vacation. When the script finishes, the infrastructure saves the resulting model weights to a storage bucket and immediately tears down the expensive GPUs so you stop paying for them.
And the sources provide a very clear heuristic for what kind of hardware you should be requesting when you submit that job. They draw a stark contrast between traditional machine learning workloads and deep learning workloads.
Yes, traditional machine learning, so algorithms like random forests, support vector machines, or standard scikit-learn models operate fundamentally differently than neural networks.
Because they don't need GPUs.
Exactly. They often train extremely efficiently on standard CPUs. They don't typically utilize the highly parallel matrix multiplication that GPUs are specifically built for.
Which perfectly explains the trap laid out in sample question 37. Listen to this setup. You built a custom ML model using scikit-learn. The training time is taking much longer than expected. You decide to migrate the model to Vertex AI Training to speed things up. The question asks, what should you try out first?
Okay, a classic scenario.
Now, my instinct, and I think the instinct of most engineers, is to say it's too slow. So I need to rewrite the scikit-learn code into TensorFlow and run it on a massive cluster of GPUs.
It's the instinct to grab a sledgehammer to drive in a thumbtack. Rewriting an entire model's underlying framework is a massive engineering undertaking. It introduces new bugs, it delays timelines, and it requires extensive validation.
Right.
The prompt specifically asks what you should try first. Because scikit-learn is inherently a CPU-bound framework, the most logical, low-effort architectural move is simply to submit the job to Vertex AI Training and request a significantly more powerful CPU compute instance.
Right. You don't change the code at all. You just drop it onto a machine with 96 CPU cores instead of 4.
Exactly. You scale vertically first. If that massive CPU still can't handle the load, Only then do you consider the massive architectural shift of rewriting the code for GPU parallelization.
Okay, so we are writing code in our Workbench sandbox. We are smartly submitting jobs to Vertex AI Training, choosing CPUs or GPUs based on the algorithm's actual physical requirements. The code is running efficiently.
Sounds like a successful pipeline so far.
It does, but this success introduces a completely new operational nightmare. Imagine a team of 5 data scientists working on a massive project. Over the course of a month, they have submitted 500 different training jobs. They've tweaked learning rates, they've altered the data sets, they've changed the neural network layers.
Oh, I know where this is going.
How on earth do you remember which specific combination of dataset and hyperparameters produced that one amazing 99% accuracy result last Tuesday?
If you don't have a rigid system you don't remember, you just described the operational reality of enterprise machine learning without governance. It's absolute chaos. Data scientists start saving models on their local hard drives, name them things like model final v3 really final.pkl.
I have absolutely seen those exact file names.
We all have. This is a phenomenon known as shadow ML. It's when critical business logic exists solely in the undocumented, untracked artifacts sitting on a random engineer's laptop.
Which is terrifying.
It is. If that engineer leaves the company, the knowledge of how that model was created literally vanishes. This is why the sources dedicate so much architecture to what we can call the artifact archipelago.
The archipelago,
Yeah.
meaning we have to meticulously separate and track every single asset onto its own dedicated island rather than just dumping everything into one massive cloud storage bucket. Let's map these islands. Where does everything physically go?
The architecture demands strict segregation. First, your pipeline definitions and your raw Python training code. That goes into a Git repository. Source control is non-negotiable. You need to track every character of code changed over time.
Right, standard software engineering. What's next?
Second, the Docker containers that execute that code live in the artifact registry. Third, the actual serialized weights and biases, the mathematical brain of the trained model, must be registered in the Vertex AI Model Registry. And finally, the metadata, the record of the learning rates used, the evaluation metrics achieved, and the specific pointers to the data sets, that all lives in Vertex ML metadata and Vertex AI Experiments.
I want to zoom in on the Vertex AI Model Registry because you mentioned shadow ML, and looking at the documentation, the registry seems to be the physical mechanism specifically designed to destroy shadow ML. It's not just a fancy folder in the cloud, is it?
Far from it. The model registry is a strict governance platform. It is the central authority for the entire lifecycle of a model. When a training job finishes, it doesn't just drop a file and walk away. It registers a versioned artifact in the registry.
So it tracks the history.
Yes, but more importantly, the registry forces documentation through something called model cards. It records exactly what the model is intended to do and its known limitations. Furthermore, it completely controls the launch process.
Meaning I can't just deploy whenever I want.
Exactly. An engineer cannot simply push a model from their laptop to a live API endpoint. The registry acts as the gatekeeper. Stakeholders can review the offline evaluation metrics stored in the registry, compare them to the current production model, and physically approve or reject the rollout based on empirical evidence. It enforces operational rigor.
It's essentially the bouncer at the door of production. And then right next to it, we have Vertex AI Experiments. If the registry is for the final, polished models, Experiment seems to be the dashboard for the messy trial and error process of getting there.
Yes, when you are hyperparameter tuning, running, say, 50 variations of models simultaneously to see which one learns best experiments, gives you a single pane of glass to visualize the loss surfaces.
So I'm not just digging through text logs.
No, you aren't digging through 50 text log
Yeah.
files. You are looking at a central dashboard that instantly visualizes which exact combination of learning rate and batch size yielded the highest accuracy. It turns guesswork into actual empirical science.
Which brings us to a concept that I think is the most profound architectural idea in this entire deep dive. It's the concept of lineage. If you think about it, lineage is basically an ancestry DNA test for your algorithm.
I really love that framing. Artifact lineage is the mathematical, provable record of every single factor that resulted in a specific artifact. An artifact could be a trained model, a pre-processed data set, or even a set of evaluation metrics.
So a model's lineage isn't just the code that built it.
No, it is much, much deeper than that. The lineage encompasses the exact Git hash of the source code executed. It includes the specific container image digest from the artifact registry. It includes the exact hyperparameter values injected into the training script. And critically, it includes the exact URI of the physical dataset used during that specific run.
Okay, but let me challenge that for a second. Why is this level of exhaustive tracking so vital? If I have the final trained model sitting in my registry and it works, why do I care about its great-grandfather dataset from 3 months ago?
Because models degrade, and when they do, you need to understand exactly why. Let's use sample question 119 to illustrate exactly how critical this is.
Okay.
Imagine you have a model in production, predicting the failure of a highly expensive critical machine part in a factory. The pipeline is designed to read data from a constantly updating BigQuery table, extract a snapshot into cloud storage in a format called TF record, train the model on that snapshot, and then deploy it.
Okay, so the underlying source data is constantly moving and changing every single day.
Exactly.
Right.
Now imagine the model in production suddenly starts misclassifying failures. It's missing critical defects. You know which version of the model is failing because the model registry tracks the deployed version. But to debug the math, you need to recover the exact physical data that this specific model was trained on.
And I can't just go run a query against the BigQuery table today because that table has had 3 months of new data appended to it and old data deleted or modified. The original state of the data is completely gone.
Precisely. The source data is dynamic. If you don't have lineage, you are completely blind. You have a failing model and absolutely no idea what it actually learned from. But the architectural solution provided in the sources is to utilize the lineage graph in Vertex AI metadata.
How does that physically work? Do I just click on the model and hit rewind?
Essentially, yes. You query the metadata graph for that specific model artifact ID. The graph visually and programmatically links that model back to the specific execution run that created it.
Okay.
You trace the edges of that graph backward to the specific pipeline step that extracted the data from BigQuery. And attached to that step, the metadata holds the exact immutable cloud storage URI and timestamp of the physical T record copy that was created on that specific day.
Wow.
You can pull that exact data set, load it into Workbench, and begin debugging the mathematical drift. You have a mathematically provable audit trail of how that model was born.
That is incredible. If you are building models at an enterprise scale, you aren't just writing code, you are building an immutable paper trail. Without lineage, you don't really have data science. You just have a black box of good luck that you can never legally or technically reproduce.
And reproducing results is the fundamental bedrock of the scientific method. If you cannot reproduce it, it isn't science, it's alchemy.
Absolutely. Okay, so we have our workbench. We are meticulously tracking our ancestry DNA through lineage and metadata. We have solved the organizational chaos. But now we have to confront the limits of physics.
Here we go.
What happens when our meticulously tracked model requires more mathematical operations than a single CPU or GPU can calculate in a human lifetime? That forces us into the realm of distributed training. We have to talk about the engine room, TensorFlow at scale, and TPUs.
When you hit the computational limits of a single machine, you have no choice but to distribute the workload. But to understand how to distribute it, you first have to understand how TensorFlow physically translates your Python code into electrical signals on a microchip. The sources provide a breakdown of the TensorFlow abstraction layers, and understanding this stack is crucial.
Right, because a Python script can't just talk directly to a graphics card. Walk us down the layers. How does a line of code become a hardware instruction?
At the very top of the stack, you have high-level APIs like tf.keras and tf.data. This is where data scientists live.
Okay.
tf.keras allows you to define a neural network by literally stacking, snapping Lego bricks together. You say, I want a dense layer with 128 neurons followed by a dropout layer. And tf.data handles the input pipeline. Moving down one layer, you find components for custom modeling, tf.losses and tf.optimizers. This is where you define how the network measures its errors and how it mathematically adjusts its weights to learn.
Okay, so the top layers are basically the architectural blueprint of the model.
Exactly. But a blueprint isn't a building. Once you define that blueprint, we drop down into core TensorFlow in Python, which translates your layers into a complex computational graph of mathematical operations. But Python is interpreted language. It's way too slow for massive matrix math.
So it has to be handed off.
Right, so that graph is handed down again to core TensorFlow in C++ space.
C++ being a compiled, highly efficient language.
Right. The C++ layer acts as the actual execution engine. It takes that graph and runs it through an incredibly sophisticated compiler, often XLA, the Accelerated Linear Algebra Compiler. This compiler analyzes your entire neural network, optimizes the math, and fuses operations together.
Then it hits the metal.
Yes. Finally, it translates those optimized operations into the specific low-level hardware instructions required by the absolute bottom layer, the physical execution hardware, the CPUs, GPUs, or TPUs.
And the beauty of this abstraction is that the data scientist at the top layer writing Keras code doesn't need to know how to write custom C++ hardware drivers for an NVIDIA GPU. TensorFlow handles the entire physical translation for them.
It's a massive quality of life feature.
Okay, so we've built our Keras model, and it's compiled down to the hardware. But the data set is 100 terabytes. One machine, even with a massive GPU, will take 6 months to process it. We need an army of machines. The architecture slides introduce 4 distinct TensorFlow distributed training strategies. Let's walk through how they physically work.
When one node isn't enough, you have to distribute the math. The first strategy is mirrored strategy. This is designed for synchronous training on a single physical node that has multiple accelerators attached to it, like a massive server with 8 GPUs plugged into its motherboard.
Synchronous, meaning they are all working on the exact same problem at the exact same time. How do they share the data? Does the CPU just chop the data set into 8 pieces?
Essentially, yes. The entire model, all of its variables and weights, is completely mirrored across the memory of all 8 GPUs. During a training step, each GPU receives a different slice of the input data batch. They all independently perform the forward pass and calculate their gradients, their proposed adjustments to the weights.
But if they all calculate different adjustments based on different data slices, how do they stay synchronized?
Before the step can finish, all 8 GPUs must pause and communicate with each other. They use a high-speed internal interconnect like NVIDIA's NVLink to rapidly average all of their proposed adjustments together. This is called an all-reduce operation. Once they agree on the exact average, they all update their internal weights identically and then move to the next step. They stay perfectly in sync.
Okay, one machine, 8 GPUs, perfect synchronization over NVLink. But what if 8 GPUs isn't enough? What if I need 800 GPUs? One motherboard obviously can't hold that.
Then you must move across the network to multi-worker mirrored strategy. This is still mathematically synchronous, but it scales across many physical nodes, each with many accelerators. So now you have 100 physical servers, each with 8 GPUs, all working together.
Okay, wait. I'm looking at this architecture, and my first instinct is that this sounds like a massive synchronization nightmare.
Oh, can be.
Because if every single GPU has to agree on the average weight update before the next step can begin, what happens if one node out of the 100 has, like, a slightly degraded network cable, and it takes an extra 500 milliseconds to send its data? Doesn't the entire cluster of 800 GPUs just sit there idling, waiting for that one slow machine?
You have just identified the fundamental vulnerability of synchronous distributed training.
Yep.
Yes, the entire cluster is constrained by the speed of the absolute slowest node. The network latency overhead of orchestrating an all-reduce operation across 100 physical servers over Ethernet switches is immense.
So is there an asynchronous way to do this, where the fast machines don't have to sit around and wait?
Yes, and that is the third strategy. Parameter server strategy. In this architecture, you designate some of your machines to act strictly as parameter servers. Their only job is to hold the master copy of the model weights in memory.
And the other machines?
The rest of the machines act as independent workers. A worker pulls the current weights from the server, calculates the gradients on its slice of data, and pushes the update back to the server.
And it doesn't wait for anyone else. It just grabs the next batch of data and goes again.
Exactly. It is highly resilient to slow nodes because everyone operates independently. However, it introduces a severe mathematical problem known as stale gradients.
Stale gradients, what does that mean?
Well, by the time a slow worker finishes calculating its update and pushes it to the server, 50 other fast workers might have already updated the master weights. The slow worker is now applying an update based on an outdated version of the model, which can destabilize the entire learning process. It requires very careful tuning to converge.
So it's a massive trade-off between hardware efficiency and mathematical stability. This perfectly contextualizes sample question 29 from our sources. Let me read the scenario.
Go for it.
I'm developing a massive transformer model in TensorFlow to translate text. The training data includes millions of documents sitting in a cloud storage bucket. I plan to use distributed training to reduce training time, but the prompt adds a strict constraint. I need to configure the training job while minimizing the effort required to modify my code and minimizing the effort to manage the cluster's configuration. How do I choose between these strategies without rewriting everything or hiring a Kubernetes administrator.
The prompt demands massive scale with minimal management overhead. The correct architectural answer is to create a Vertex AI custom training job with GPU accelerators and implement tf.distribute multi-worker mirrored strategy within your Keras code.
Why that specific combination? If multi-worker has the stalling vulnerability we just talked about, why is it the right choice here?
Because of the minimal effort constraint. By submitting this as a Vertex AI custom training job, you completely offload the cluster management. You don't have to manually provision 100 VMs, install drivers, or configure the highly complex Kubernetes pod networking required for the nodes to discover each other.
Vertex AI just handles it.
Vertex AI handles the entire physical topology automatically. And on the code side, multi-worker mirrored strategy is natively integrated into Keras. You essentially wrap your model compilation step inside the strategy's scope context manager, and TensorFlow automatically handles the complex ring-all-reduced communication protocols between the servers. You achieve massive synchronous scale with literally 3 extra lines of Python code.
It's abstracting away the infrastructure pain, but let's look at a scenario where we actually want to get our hands dirty at the hardware level. Sample question 98. You work with a team of researchers developing state-of-the-art algorithms for financial analysis. Your team develops and debugs complex, novel models in TensorFlow. You want to maintain the tactile ease of debugging while also drastically reducing the model training time.
When the prompt specifies state-of-the-art, complex models, and a need to drastically reduce training time, it is signaling that traditional GPUs might not be the optimal architecture. You should be looking at the 4th distributed strategy, PPU strategy, which runs on Google's tensor processing units.
Now, you briefly mentioned earlier that TPUs are ASICs application-specific integrated circuits. What does that actually mean mechanically? Why is a TPU different than the CPU in my laptop or the GPU in my gaming rig?
A CPU is a general-purpose processor. It can run an operating system, it can render a web browser, it can do a little bit of everything, but it executes instructions sequentially. A GPU has thousands of tiny cores, making it great for parallelizing tasks like rendering millions of pixels on a screen. But a TPU is an ASIC. It is hardwired at the literal silicon level to do exactly one thing: massive matrix multiplication. It uses an architecture called a systolic array, where data physically flows through a massive grid of arithmetic logic units, performing hundreds of thousands of multiply and accumulate operations per clock cycle without needing to constantly read and write to memory. For the right neural network architectures, TPUs offer orders of magnitude faster training.
Okay, so the hardware is terrifyingly fast, but the prompt also emphasizes maintaining the ease of debugging. If I'm submitting jobs to a mysterious cluster of ASICs in the cloud, how do I debug a complex financial algorithm when it inevitably crashes on line 42?
That is the historical friction with cloud training. You submit a job into a void, wait 20 minutes for it to fail, and then try to decipher a massive text log file. It destroys developer velocity. So the architectural solution for this specific scenario is to configure a cloud TPU VM and then literally SSH directly into that virtual machine.
SSH, like logging into an old-school bare metal server in a basement.
Yes. Cloud TPU VMs completely changed the architecture. Previously, your code ran on a separate CPU host machine over the network from the TPU. Now, you can SSH directly into the host machine that is physically connected to the PPU board via PCI Express.
So you are right there on the metal.
You are inside the machine. You can run your Python scripts interactively in the terminal, step through the execution line by line, inspect the tensor shapes in real time, and debug with the immediate tactile feedback of local development, all while having direct access to the immense power of the systolic array.
It gives researchers the intimacy of a local laptop with the raw power of a supercomputer. But with that raw power comes a lot of nuance. Let's look at sample question 132.
All right.
You're training an ML model on a large data set using one of these massive TPUs. You expect it to be lightning fast, but you notice the training process is taking much longer than expected. You dig into the profiling metrics and discover that the TPU is barely reaching 20% of its utilization capacity. It's basically idling.
Yeah, that happens a lot.
The question asks, what should you do? Now, my first guess would be that the learning rate is wrong. Maybe it's taking too small of steps and is crawling through the data.
It's a logical guess, but it confuses mathematical convergence with physical hardware utilization. If a TPU is idling, it means it is starving for work. The systolic array is like a massive, highly automated factory floor with 100,000 robotic arms.
Okay, I like this analogy.
If your code only sends one tiny widget down the conveyor belt at a time, 99% of the robotic arms will just sit there waiting. Changing the learning rate just changes how the widget is assembled. It doesn't put more widgets on the belt.
Okay, so how do I flood the factory floor?
The correct answer is to drastically increase the batch size. The batch size dictates how many physical examples, how many rows of data, or how many images you feed into the model's forward pass before it stops to calculate a gradient update.
So you give it more to do at once.
By drastically increasing the batch size, you send a massive contiguous block of data to the TPU all at once. The TPU can parallelize the matrix math for all of those examples simultaneously across its entire array of cores.
You feed the beast faster. The utilization spikes to 95%, and the overall time to process an epoch plummets.
Exactly. It's a counterintuitive fix for some passes. You want the overall job to go faster, so you actually give the machine a much heavier load to carry per individual step. But because of the deeply parallel architecture of the ASIC, heavier loads utilize the silicon vastly more efficiently.
It's like switching from a fleet of minivans to a massive freight train to move cargo. The train takes a massive amount of cargo at once, but it utilizes the rails vastly more efficiently than thousands of vans causing traffic.
That is a perfect analogy.
But that freight train analogy perfectly sets up our final and perhaps most critical architectural challenge, because even with distributed GPUs, massive TPU arrays, and perfectly tracked lineage, the laws of physics eventually get in the way.
They always do.
Eventually, the bottleneck isn't the ability of the microchip to crunch the math. The bottleneck is the physical act of moving the data from the hard drive over the network and into the chip's memory to feed that massive factory. Let's talk about breaking bottlenecks, the reduction server and data I/O.
The input-output bottleneck is the silent killer of enterprise machine learning. It absolutely does not matter if you have 100 of the fastest GPUs on the planet. If they spend 90% of their time just sitting idle, waiting for the storage drive to hand them the next piece of data.
Right.
Slide 36 of the sources calls this out explicitly, noting that the exponential growth of datasets has caused data ingestion to become one of the primary roadblocks to scaling.
And we have two sample questions that attack this exact problem from the storage side. Question 44 and question 122, let's combine them, because they are exposing the exact same physical limitation.
Okay, let's hear the setup. You are developing a massive image classification model. You have millions of raw JPEG images sitting in a cloud storage bucket. You want to read these images at scale during your distributed training loop, but you absolutely must minimize data I/O bottlenecks. Now, intuitively, I would just point my TensorFlow script to the cloud storage folder and say, read these images. Why is that a catastrophic mistake? Why is a tiny 50 kilobyte JPEG file hard for a supercomputer to read? Because of the massive overhead of network protocols and disk seek times. When you read a single file from cloud storage, the system has to initiate a TCP/IP connection, perform the handshake, locate the physical sectors on the storage disk where that 50 kilobyte file lives, read it, and then close the connection.
Which takes what? A few milliseconds?
Doing that once takes milliseconds, sure. But doing that 1 million times randomly across a storage cluster creates an immense amount of I/O latency. The time spent opening and closing connections vastly outweighs the time spent actually transferring the bytes.
So you can't just load a freight train with a million loose pebbles. You'll spend all day picking them up one by one. What is the architectural solution to package them?
You have to change the physical format of the data before training even begins. The solution prescribed across both questions is to orchestrate a dataflow job prior to kicking off your Vertex AI training. Dataflow is Google's massively parallel data processing service.
Okay, and what does Dataflow do to the images?
You use it to read all those individual JPEGs, decode them, and serialize them into a much smaller number of massive sequential files called TIFF records.
What exactly is a TIFF record physically? Is it just like a zip file?
No, it's not compressed like a zip file. A TIFF record is a simple record-oriented binary format native to TensorFlow. It uses protocol buffers to serialize the data. Instead of a million tiny JPEG files scattered across a hard drive, Dataflow packs them into, say, 100 massive TIFF record files, each containing 10,000 images laid out sequentially in binary code.
How does that solve the network handshake bottleneck, though?
Because when training begins, TensorFlow uses the tf.data, T-record dataset API. Instead of making a million random network requests, the system opens a single connection to one massive T-record file and just streams the binary data sequentially. It prefetches the data into memory blocks in the background while the GPU is processing the current batch. You convert the I/O pattern from a million chaotic random reads into a smooth, continuous fire hose of sequential data.
And the GPUs stay fully saturated.
Exactly. They never have to wait.
Okay, so we've solved the storage I/O bottleneck. Our T records are streaming inefficiently. But there is a second, even more complex bottleneck when you are doing distributed training across dozens of nodes, and it has to do with how the machines actually talk to each other.
Yes, the network communication bottleneck. Remember when we dissected the multi-worker mirrored strategy? Synchronous distributed training across multiple servers.
Right, where every GPU computes its proposed updates, and they all have to pause and average their results together in that all-reduce operation before the next step can start.
Exactly. When you have 8 GPUs on one machine, they communicate over the internal motherboard via NVLink, which is incredibly fast. But when you scale out to 100 GPUs across 12 different physical servers, that massive all-reduce operation has to happen over the data center's Ethernet network.
Which is much slower.
And as you add more GPUs to speed up the math, the sheer volume of network traffic required to synchronize those gradients scales quadratically. The network bandwidth becomes totally congested, the latency spikes, and suddenly, adding more GPUs actually makes the training slower because they spend all their time waiting on network packets.
So the local roads are completely jammed with delivery trucks trying to talk to each other. And this is where Google Cloud introduces a highly specific proprietary architectural feature on slide 36, the reduction server. How does it clear the traffic jam?
The reduction server is just a brilliant piece of infrastructure engineering. It fundamentally alters the topology of the all-reduce operation for NVIDIA GPUs. Instead of every GPU trying to talk to every other GPU in a chaotic peer-to-peer web across the network switches, Google introduced a dedicated tier of worker nodes, the reduction servers.
So these are extra machines added to the cluster. What hardware are they running?
That's the genius part.
Yes.
They are strictly CPU-based machines, highly optimized for network bandwidth and latency. They do not have GPUs attached. Their entire purpose is to offload the aggregation math.
So they just do the averaging?
Yes. The expensive GPU nodes quickly stream their proposed gradients to the reduction servers. The reduction servers efficiently average the data together using their optimized CPUs and network interfaces, and then broadcast the final synchronized weights back to the GPUs.
It's like taking all the delivery trucks off the chaotic local rows and building a dedicated high-speed rail network just to move their cargo. The trucks just drop their cargo at the station and get back to work.
Precisely. The GPUs spend vastly less time managing network packets and more time crunching matrix math. And the slide provides some astonishing hard numbers from a real-world test. An engineering team was fine-tuning a massive large language model, a BERT architecture. By adding 20 of these CPU-based reduction server nodes to their existing GPU cluster, they increased the physical training throughput, so the steps executed per second by 75%.
Okay, 75% faster is a massive leap in engineering performance. But here's the paradox we opened the show with. The slide also claims that by adding these 20 additional servers to the architecture, the cost per step was reduced by 42%.
Yep.
Adding 20 massive servers somehow reduced the cloud bill by nearly half. How does spending more money on extra physical hardware actually save money?
It forces you to look at the math of time versus unit cost. Cloud economics are heavily skewed by the astronomical cost of renting GPUs. Let's say a massive GPU node costs $30 per hour to rent, and you have 10 of them. That's $300 an hour. But CPUs, which power the reduction servers, are relatively cheap, maybe $1 or $2 an hour.
Okay, so the base cost is heavily weighted to the GPUs.
Right. In the baseline scenario without reduction servers, those expensive GPUs are spending a huge percentage of their billable hour just sitting in network traffic, waiting for the peer-to-peer all-reduced to finish. You are essentially paying top dollar for a Ferrari to idle in a traffic jam.
You are burning cash on latency.
Exactly. When you bolt on those 20 cheap CPU reduction servers, you completely eliminate the traffic jam. The throughput increases by 75%. This means the massive, expensive GPU job that would have taken 100 hours now finishes in roughly 57 hours.
Ah, I see the math now.
Yes. Your hourly burn rate is slightly higher because you are paying a few extra dollars an hour for the CPU nodes, but you are renting the $300 an hour GPU cluster for 43 fewer hours. The massive reduction in total billable GPU hours exponentially outweighs the minor cost of the extra CPU nodes, leading to that massive net savings of 42% per step.
That is just wild. You are strategically deploying cheap logistics hardware to maximize the utilization of your heavy machinery. And this maps perfectly to sample question 1 in the sources. You are training a custom language model and plan to use the reduction server strategy. You have to configure the worker pools in Vertex AI. How do you physically architect it?
The correct configuration perfectly reflects this physical separation of concerns. In Vertex AI Custom Training, you configure the first two worker pools, the master and the workers, to use your expensive GPU machine types and load your actual model training code.
Then the third pool.
Then you configure a third worker pool, which represents the reduction servers. Crucially, you use the specific Google-provided reduction server container image for this pool. You do not attach accelerators to this third pool because they only need CPUs to move data, and you specifically select a machine type that prioritizes high network bandwidth over raw compute power.
You architect the high-speed rail. What an incredible journey we've been on today. We've constructed a massive enterprise-scale machine learning operation from the ground up. Let me try to synthesize this architectural blueprint. We started by mapping the ML spectrum, realizing that while AutoML is powerful, full custom training is the required bulletproof tailored suit when we need granular control over novel topologies or massive scale.
That was step one.
We physically separated our environments, using Vertex AI Workbench as our secure IAM-authenticated development sandbox, leveraging magic commands to query BigQuery without moving data, and instantly injecting dependencies into our user directories to maintain developer flow.
And we didn't stop at development. We confronted the operational nightmare of shadow ML by building an artifact archipelago. We learned that the model registry isn't just a storage folder, it is a physical governance gatekeeper. We leveraged Vertex ML metadata to construct the lineage graph, giving us a mathematically provable ancestry DNA for every model, allowing us to trace a production failure back to the exact cloud storage URI of the T-record dataset it was trained on.
From there, we dove down into the engine room, decoding how Python scripts compiled down through C++ into physical hardware instructions. We navigated the treacherous waters of distributed training, understanding why the synchronous ring, all-reduce of multi-worker mirrored strategy is vulnerable to slow nodes, and how TPUs use systolic arrays to process massive batches of data.
And finally, we broke the laws of hardware economics, using data flow to stream binary T records, and deploying CPU reduction servers to eliminate GPU network traffic, cutting our total cloud bill by nearly half.
So what does this all mean? We've given you the blueprints, we've shown you how the physics of the cloud actually operate, but I want to leave you with one final thought, zooming out from the hardware and looking at the philosophy of what we're actually building here.
If we synthesize all of this infrastructure, a really profound realization emerges about enterprise value. The industry is currently totally obsessed with the models themselves. Companies genuinely believe their most valuable asset is that serialized file of weights and biases sitting in the registry. But if you look at the architecture we just built, the intense focus on Vertex ML metadata, the exhaustive tracking of lineage, it suggests a completely different reality.
How so?
A model is inherently fragile. It is merely a temporary mathematical manifestation of the data it saw on a specific day. Data drifts, consumer behavior changes, and tomorrow, that highly optimized model might become entirely obsolete or wildly inaccurate.
That's true, the world changes.
So the model itself is not the true asset. The true asset is the lineage. It is the immutable, meticulously tracked historical record of exactly how that model was born. If you lose the model but you have the lineage, you can perfectly rebuild it, adapt it, and scale it. But if you have the model and you lose the lineage, you have nothing but an inscrutable black box of temporary math.
That is a phenomenal perspective. The code only tells you what the machine is today. The lineage is the institutional memory of what the machine experienced to get there. It is your only path to debugging reality. So as you walk back into your engineering stand-ups and you look at your cloud architecture diagrams, remember, you aren't just writing code to execute a mathematical function. You are architecting the immutable history of your organization's intelligence. The blueprints are in your hands. Build something extraordinary.